Hi, we're here today at Target to look for some rare bioluminescence. Oh hey, look at that, found some. Hey, you guys got any luciferin? I'll show you mine if you show me yours. You guys want to trade? I don't think they want to trade. We'll keep looking.
To understand bioluminescence, first one must understand the overall chemiluminescence that may occur. Now, chemiluminescence is any chemical reaction resulting in the emission of light. Generally speaking, in bioluminescence, an enzyme or a luciferase catalyzes the oxidation of a substrate, also known as a luciferin, and then causes it to become excited. And then when the excited state goes back down to the ground state, this results in the emission of light. Bioluminescence is specifically when chemiluminescence occurs in living things. It may occur in animals such as jellyfish, fish, or lightning bugs, for example, but it also can occur in plants or protists or other single-celled organisms such as algae or dinoflagellates.
Now, this isn't to be confused with phosphorescence and fluorescence. In phosphorescence, a material absorbs radiation at one wavelength and then it slowly emits it, generally at a less energetic wavelength. This may be in the visible spectrum, but it does not have to be. In fluorescence, radiation is absorbed by a material and then it is immediately emitted. The main difference between fluorescence and phosphorescence is simply the time it takes to re-emit that wavelength.
Now, the most understood bioluminescence and the most researched bioluminescence is firefly bioluminescence. Now, the luciferin for fireflies is D-firefly luciferin, and the luciferase will generally refer to it as just simply a luciferase. Taking a look at this mechanism, you can see that most of the chemistry occurs on and around the carboxylic acid group on the rightmost part of the molecule. Now, if you take this molecule, ATP, and magnesium ion, combine it with a luciferase, the result of the first step of the reaction is the carboxylic acid is converted to its analogous adenosine monophosphate ester and pyrophosphate as a byproduct. The next step is the deprotonation of the carbon adjacent to the carbon of the ester, resulting in a tertiary anion. After this, oxygen oxidizes the rightmost part of the molecule, which results in the formation of a new heterocycle with two adjacent oxygens and two adjacent carbons and a carbonyl on the corner carbon. With the loss of carbon dioxide, you get oxyluciferin. Now, this is where it gets to be a little bit tricky. This molecule can take on a few forms. First, I'll refer to as a phenol keto or a phenolate keto or a phenol enol, or a phenolate, enolate, etc., based off the leftmost phenol and the rightmost heterocycle. Now, this keto can tautomerize into an enol, but it's unclear whether this enol is deprotonated or not to an enolate. Additionally, the phenol on the leftmost side may also become a phenolate. However, Snellenberg et al. Determined the light emission is largely caused by the excitation and emission from the phenol keto and the phenol enolate molecule forms. The phenol keto, when it's excited and goes back down to its ground state, this results in the emission of red light. For the phenol enolate, the excitation and return to its ground state results in the yellow-green light.
What is it?
It's so pretty.
It's bioluminescence.
You just saw the clip during Finding Nemo when Marlin and Dory ran into an anglerfish. And an anglerfish is a perfect example of bioluminescence. The anglerfish, as you saw, has a dorsal ray that goes over the fish's mouth, and the tip, called an esca, produces the light. Now, this light is primarily used for luring prey. In fact, the anglerfish can actually swallow other fish that are twice its body size by unhinging its jaw, kind of like a snake, and swallowing it whole. The other use for the light is mating. Only female anglerfish have that esca at the tip of their dorsal ray. And not a whole lot is known about the anglerfish because it's so hard to get to. It lives in the deepest recesses of the ocean. But it's speculated that the bioluminescence is caused by a bacteria that enters the esca through pores, and once that density becomes high enough, the Esca will start to glow. The next animal we had on our list is the lanternfish. Now, a lot of people don't know what the lanternfish is, but it actually looks a lot like an anchovy. If you've ever seen those gross, like slimy, thin fish, the lanternfish is basically the exact same, except it glows on its head, tail, and on the belly. The lanternfish actually make up 65% of all deep sea fish biomass, which is approximately 550 to 660 million metric tons. That's approximately 1,600 Empire State Buildings or 100 Great Pyramid of Gizas. Now, the lanternfish glows a bluish green color, and the glowing is primarily for communications, whether that be courting or a term called shoaling, which is where groups of fish communicate to each other to decide where they're going to go. It's also used as camouflage in something called counterillumination, which is when the lanternfish matches the ambient light that's being produced around it, making it virtually invisible.
One simple but pretty neat group of organisms that exhibits bioluminescence is the dinoflagellates. These single-celled plankton range from 30 micrometers to 1 millimeter in length, but when found in high concentrations, these tiny creatures produce a lot of light. Dinoflagellates' light emission is stimulated by mechanical stress. In nature, this stress comes from fish, but they can also be stimulated by boats and people. The light is emitted less than 20 milliseconds after the stimulus is present, making it one of the fastest known biological responses. These organisms can produce several flashes of light in a night, but it's possible for them to be overstimulated and oxidize all of their luciferin. They will regenerate luciferin over the course of the day and be ready for action again the following night. The reason for the light emission is still under question, but there are a couple hypotheses. The light may startle predators, acting as a self-preservation tool. Another theory is that the light actually attracts even larger fish to eat the predators of the dinoflagellates. These little creatures are found virtually all over the oceans, but occasionally the conditions in an area make it possible for a higher concentration of these organisms to exist, forming what is called a red tide. Red tides often come and go, but in a few places they have been sustained for a long period of time. There are known areas in Australia, Thailand, Japan, and Tasmania, just to name a few, that contain high concentrations of bioluminescent dinoflagellates. Puerto Rico has especially good conditions, boasting 3 bioluminescent bays around the island. These sites have attracted a lot of tourism. It's possible for tourists to kayak the bay and even swim or snorkel there. The sparkling, simulated dinoflagellates are absolutely breathtaking, but please, no flash photography.
A great way to see bioluminescence in your own home is to start your own colony of dinoflagellates. The first thing you'll need to do is gather the materials. You'll need a growing container. A 500 milliliter flask works well for this. Sea salt, but not just any sea salt. You have to get this from a pet store. You can't just use like the Morton salt out of the cabinet. You'll need a grow light and timer. Microalgae grow, which is the food that the bacteria will use to thrive. A starting culture, because you can't just throw some salt in a bucket of water and expect algae to grow. You will also need distilled water and a hydrometer, which measures specific gravity. After you have gathered the materials, the first step is to wash everything really well, especially the flask. Some say to swirl diluted bleach in it, and others say to microwave it for a short period of time. Either way works, but you just have to make sure that everything is really clean. Next, mix the sea salt into the distilled water until it has a specific gravity of 1.019, and you can use the hydrometer to measure the specific gravity. Add about 1 milliliter of microgrow algae into the salt water. You can also just buy the culture solution if you're lazy and don't want to make your own. Let the solution and the cultures sit for an hour or two together in a place out of the sun so that they can reach room temperature. Don't let the cultures experience a sudden change in temperature, or it could significantly harm them. Ideal temperature is about 22 degrees Celsius, which is room temperature. After letting them sit, transfer the algae into the solution. The algae need a constant cycle of light and dark for the best growing results. Put the container in a dark place, a basement or closet, and set up the grow light with a timer so that it turns on and off every 12 hours. So it should be in the light for 12 hours and then in the dark for 12 hours and then repeated. Monitor the cultures for color change and swirl them daily to deter sediment buildup. The algae only light up during the night cycle, so plan when you set up the timer accordingly so that you can actually see them glow. And there you have it. That's how you have your very own bioluminescent algae.
As scientists continue to research bioluminescent organisms, they are beginning to find ways that bioluminescence can be applied to other areas. One of the most useful applications is in vivo imaging. Biomedical research is working on attaching various luciferases to cells, proteins, or pathogens so that their molecular paths and processes can be tracked. Once the tagged molecule is in the body, the corresponding luciferin can be added locally to cause the emission of light. This low-level light can be detected through body tissue. So far, this procedure has been performed only on small creatures like mice, but it will hopefully be expanded in the future. And last but not least, the most famous bioluminescent creature of all.